Edro 3, 17 a.m., North Atlantic, 1942. The steel deck of the USS Corrie, a Gleaves-class destroyer, is slick with freezing spray. It bucks and shudders, a tiny patch of sovereign metal in a hostile ocean. On the bridge wing, Lieutenant Commander Elias Thorne grips the rail. He is not a line officer. He is an engineer, an observer from the Bureau of Construction and Repair, and he is freezing. His job is not to find the enemy U-boat. His job is to listen. He wears a heavy set of hydrophone headsets, the cable running to a specialized amplifier. The sonarman inside the hut scans for the ping, ping, ping of reflected sound. Thorne listens for something else. He listens for the sound of failure. He is listening for the sound of an American submarine dying. Sight start. Last week, the USS Grunion was lost with all hands. Sight 5. The Corrie had been in the support group. The after-action report was thin. Lost contact 0921. But one sonarman filed a supplemental, heard anomalous noise, a wrench, a pipe crushing, before the final report. Thorne is here because the Navy's new Gato-class boats, the pride of the fleet, are proving fatally noisy. They are supposed to be the apex predator, but they are dying in the deep. The German boats dive deeper, run quieter. The British are pragmatic, building smaller, simpler boats. The Americans have built a high-tech marvel that seems to be tearing itself apart. Thorne adjusts the gain on his amplifier, the static hissing. He is listening for the sound of a rivet popping at 300 feet. He is listening for a bulkhead buckling, a sound that rings through the water for miles. He is listening for the acoustic signature of his own failure. The tension on the bridge is a physical thing, thick as the fog. The destroyer's captain is hunting, focused on the kill. Thorne is focused on the flaw. The Gato boats are masterpieces of engineering, rated for 300 feet. But commanders, desperate to escape the sonar nets of destroyers, are pushing them to 350, even 400 feet, and they aren't coming back. The problem isn't the pressure hull, the thick cylindrical tube where the crew lives. Thorne's calculations have confirmed that hull is strong. The problem is everything else. The problem is the vast, complex array of tanks, pipes, and voids outside that pressure hull. The external fuel bunkers, the ballast tanks, the superstructure. They are made of thinner steel. They are not designed to hold back the ocean, and when they collapse, they announce the submarine's position to every listening ear in the Atlantic. Thorne closes his eyes, filtering the sound of the Corrie's own engines. He's waiting for the pop, the crunch, the sound of a design flaw becoming a tomb. Back at the Portsmouth Naval Shipyard in New Hampshire, the air smells of welding flux and low tide. Thorne stands over a set of blueprints, the massive 300-foot-long cross-section of a Balau-class boat stretching across 3 tables. The Balau is the next generation, intended to fix the Gato's flaws, but the core design is the same. He traces the lines of the external fuel bunkers. They are free-flooding on top, but designed to hold fuel against the sea. As the diesel engines drink the fuel, a void is left, an empty space, an air-filled pocket that the Atlantic at 400 feet tries to crush with a force of over 170 pounds per square inch. The shipyard is a hive of activity. Men are riveting, welding, moving steel. But Thorne is motionless, lost in thought. The sonarman's report haunts him, a crunching sound before the big bang. This is the mystery. The pressure hull fails catastrophically, a sudden implosion. But the warning sound, the thing the destroyers are hearing, comes first. It is the sound of the non-structural parts of the boat giving way. The fuel tanks sitting outside the crew's compartment are buckling. They are the acoustic betrayal. He watches two yard workers move a simple 55-gallon steel drum. One of them idly kicks it, and the empty drum dents easily. Later he sees the same worker cleaning another drum. He's filled it to the brim with water from a hose. The thin metal walls, now supported by the incompressible water inside, are rigid. The worker kicks it. The drum doesn't budge. Thorne stares. He looks at the blueprints, then back at the water-filled drum. The problem is not the steel. The problem is the nothing, the void, the differential pressure. What if the tanks were never empty? What if, as the fuel was used, something took its place, something as heavy, as incompressible as the sea itself? The idea is heresy. You build a submarine to keep the water out, but the thought takes root, a dangerous, counterintuitive spark. What if the solution to catastrophic pressure was to invite it in? What he didn't know was that this absurd idea, born from watching a yard worker and a steel drum, would change the war in the Pacific. The problem is laid bare in a cold, statistical report from the Bureau of Ships, dated October 1942. Subject: acoustic performance and structural failures, Gato-class fleet submarines. The report is a damning collection of field data. The operational test depth for the class is 300 feet. Yet German Type 7C U-boats are confirmed to be operating at depths exceeding 700 feet. American boats are being detected and hunted at depths their commanders believe are safe. Report USS Trout, SS-196, sighted enemy destroyer, dived to 350 feet. Experienced catastrophic failure of external ballast tank piping. Loud noise reported, resulting in sustained depth charging. Recommend immediate review of all external fittings. The Navy's entire Pacific strategy hinges on aggressive long-range submarine patrols. But the boats are proving to be fragile. The core of the issue is a design compromise. To maximize range, the Gato-class boats carry a huge amount of fuel in external tanks, tanks built outside the strong circular pressure hull. These tanks are shaped to be hydrodynamic, conforming to the outer skin of the submarine. They are not circular. They are made of relatively thin 1/4-inch steel plate. They are not designed to withstand the crushing pressure of the deep ocean. The designers assumed they wouldn't have to, but as the diesel engines consume the fuel, they leave behind an empty void. At 400 feet, the sea exerts nearly 25. 0 pounds of force on every square foot of that empty tank. The tank, predictably, buckles. The noise is described in one report as a gunshot in a cathedral, a sharp metallic bang that renders the submarine's silent running completely pointless. The War Office is demanding a solution. The shipyards are already working 24 hours a day. The obvious fix is to make the external tanks stronger. Reinforce them, use 1-2-inch steel. But this adds hundreds of tons of weight to the submarine. It reduces its range, slows its dive time, and requires a massive redesign that would halt production for months. The war will not wait. Other reports stream in. It's not just the fuel tanks, it's the external compressed air lines, the ballast tank flood ports, the superstructure itself. Anything with an air pocket inside it, outside the main hull, is a potential noisemaker. The fleet submarine, the most expensive and complex weapon in the U.S. arsenal, has an Achilles heel. It is being betrayed by its own empty spaces. Sight start. The data in the Buship's reports translates to human suffering. Sight 3. It means crews deep in enemy territory are trapped. They cannot dive where the enemy cannot follow. Every commander, his knuckles white in the red glow of the control room, knows that 300 feet is not a test depth, it is a cliff. Pushing past it is a gamble. They can hear their own boat protesting. The groans and pops of the outer hull are the ship's own voice, telling the Japanese destroyers above, "Here I am." Morale in the submarine force is brittle. The torpedoes don't work, and the boats are noisy. The cold, logical reality is that the US submarine is, in many ways, an inferior weapon to its German counterpart. This feeling of impossibility is formalized at the David Taylor Model Basin. Engineers in a massive test tank subject a scale model of a Gato-class midsection to simulated deep-sea pressure. They watch through thick quartz viewports as the pressure gauge climbs. At the equivalent of 380 feet, the external fuel bunker, beautifully painted in navy grey, simply vanishes. It buckles inward with such speed that it is invisible to the eye. The resulting thump shakes the concrete floor of the test facility. The pressure hull itself is fine. It holds to 700, 800 feet. But it doesn't matter. The boat is sunk the moment it makes that sound. The official recommendation from the test board is bleak. Submarine commanders must be ordered to strictly adhere to the 300-foot operational limit. It is a death sentence for aggressive patrol tactics. Experts agreed the problem was fundamental to the design. It couldn't be done. If you find the hidden stories of engineering that changed history compelling, follow us as we dive deeper into the minds of the people who defied the impossible. Lieutenant Commander Elias Thorne is not a submariner. He is 38 years old, a quiet, bespectacled man who prefers slide rules to social gatherings. He is a civil engineer, graduated top of his class from MIT. Before the war, he wasn't designing weapons, he was designing dams. He was one of the lead hydraulic engineers for the Bonneville Dam project, a man who intimately understood the colossal, indifferent force of water. He understands that water is not compressible. He knows that pressure is a function of depth and that it pushes in all directions equally. He was pulled from his civilian life into the Bureau of Yards and Docks and later seconded to BUC&R, precisely because he thinks about steel and water differently than the naval architects. The shipbuilders see a submarine as a ship that goes under. Thorne sees it as a tunnel being lowered into a reservoir. He spent years calculating load distribution on concrete spillways and intake tunnels. He knows that the only way a thin-walled pipe can survive at the bottom of a 300-foot deep lake is if it's full of water. The pressure inside equals the pressure outside. The differential is zero. The structure, no matter how thin, feels no strain. This principle, so basic to his world of civil engineering, has been completely overlooked by the naval architects, who are obsessed with buoyancy, weight, and keeping the water out. His personality is one of meticulous, almost obsessive observation. He doesn't like guesswork. He distrusts the "it's good enough for government work" mentality of the frantic wartime shipyards. Sight start, he is haunted by the Grunion. Sight 5, he sees the faces of the 70-man crew he never met. He sees the problem not as a tactical limitation, but as a mathematical error. And it is an error he believes he can solve. His mind, trained to manage the pressure of the entire Columbia River, now turns to the pressure of the North Atlantic. The problem is the same. The solution, he thinks, must be too. Thorne is in his cramped office at Portsmouth, sketching on the back of a requisition form. He draws a simple U-tube manometer. He draws the cross-section of the external fuel tank. He labels fuel oil, speed 092, and seawater, speed 1025. The oil is lighter than the water. It will float. The insight is so simple it feels stupid. What if you just let the seawater in at the bottom of the fuel tank as the fuel is drawn out from the top? The tank would remain 100% full at all times, first with fuel, then with a growing layer of seawater at the bottom, pushing the usable fuel up. The pressure inside the tank would always be identical to the ambient sea pressure outside. No differential, no void, no collapse. He takes his sketch to his superior, Captain Reynolds, a man who has built destroyers for 20 years. Reynolds looks at the drawing, his brow furrowing. Let me get this straight, Thorne. You want to intentionally flood our fuel bunkers with corrosive salt water? Thorne nods. Yes, sir, we replace the consumed fuel with seawater. The tank stays full, the pressure equalized. Reynolds throws the sketch on his desk. That's the stupidest thing I've ever heard. First, you're introducing hundreds of tons of dead weight. You'll ruin the boat's trim. Second, you'll get salt water in our diesel engines. You'll kill the boat faster than the Japanese. The Balau is a $10 million asset, not one of your MIT lab experiments. Get out of my office. Thorne stands his ground. The weight is a wash, Captain. The seawater weighs only slightly more than the fuel it replaces. It's a buoyancy problem we can trim for. As for contamination, a simple standpipe on the fuel uptake, raising it a few feet off the tank bottom, ensures we only draw fuel, not the water below it. Reynolds is furious. It's insane. The proposal is denied. Thorne picks up his sketch. He knows the math is right. If the Bureau won't authorize it, he'll find a way to test it himself. Thorne knows he can't requisition a submarine for a forbidden experiment. He needs a smaller, secret test. He finds an ally in Chief Mulligan, the grizzled 60-year-old civilian foreman who runs the shipyard's pressure testing facility. Mulligan is a legend in the yard, a man who has built boats since before the last war. He too has read the reports from the Pacific. He has sons on destroyers. He hates sending men to sea in flawed machines. Thorne finds him in the pressure pit, a massive water-filled concrete bunker where sections of hull and piping are tested to failure. "Chief," Thorne says, laying his simple sketch on a workbench, "I need to test a fuel tank, but I need to test it full." Mulligan looks at the sketch, then at Thorne. He understands the principle instantly. "You're gonna let the sea in to balance her." Thorne nods. "The captain thinks I'm crazy." Mulligan grunts, wiping grease from his hands. "The captain ain't the one listening to the reports from the canal." "All right, Lieutenant, we'll do it. But we do it at night. Officially, we're running a structural test on a scrap baffle plate. They find what they need in the scrap heap, a salvaged external tank section from the USS Deepe, which had been damaged in a collision. It is bent, but it will serve. Over 2 nights they work by the dim glow of welding arcs. The air is cold, filled with the smell of ozone and damp concrete. They weld the tank section shut, fitting it with 2 pipes. One at the bottom they leave open. This is the seawater inlet. One at the top they connect to a hose, the fuel uptake. They fill the tank with 90% diesel oil and 10% water, just to prime the system. Then they lower the entire assembly into the massive cylindrical test chamber. Thorne and Mulligan stand at the control panel, a bank of heavy brass gauges and iron wheels. They seal the main hatch, the clang of steel echoing in the chamber. "All right, Lieutenant?" Mulligan says. Let's fill the pot. He opens the valve, and the high-pressure pumps whine to life, flooding the chamber, simulating the ocean's descent. Their first test is a control. They secure a standard empty tank section in the chamber, just as it would be on a Gato boat. They seal the hatch. Taking her down, Mulligan says. The needle on the main pressure gauge climbs. 100 pieces, 120, 150, 330 feet. A microphone inside the test tank transmits the sound, a high-pitched scree of protesting steel. At 178 psi, the equivalent of 401 feet, the speaker explodes with a deafening crack boom. The shockwave shudders the concrete floor. Mulligan turns the valve, the pumps reversing. She's gone, just like they said. They drain the tank, and the mangled, imploded wreckage of the steel tank is all the proof they need. Now for Thorne's test. They hoist out the scrap and lower their modified tank. The one filled with oil and water. They dog the hatch. The air is thick with anticipation. All right, Mulligan says, his hand on the valve. Here we go. The pumps whine. The gauge climbs. 150 psi, silence. 200 psi, 450 feet. The only sound is the hum of the pumps. 250 psi, 560 feet. Nothing. Thorne and Mulligan stare at the gauge, not breathing. 300 psi, 675 feet. 350 psi, 788 feet. The needle passes the point where the German U-boats operate. 400 psi, 900 feet. The needle stops. The tank is holding a pressure that would crush a Gato boat's pressure hull, and it is doing it in total silence. Thorne feels a wave of adrenaline, a profound sense of rightness. The thin steel walls of the tank aren't fighting the pressure, they are ignoring it. The 400 psi outside is perfectly balanced by the 400 psi of incompressible fluid inside. Mulligan lets out a long, slow breath and just whispers, "Son of a bitch." He looks at Thorne, a new respect in his eyes. "You did it, Lieutenant. You just made the silent service." Silent. The breakthrough is not a new alloy or a thicker hull. It's a new idea. If stories like this fascinate you, stay with us. The next chapter of wartime innovation might surprise you. The success in the test pit is one thing. Convincing the admirals in Washington, D.C. is another. Thorne is summoned to a tribunal at the Bureau of Ships. He stands alone in a dark, wood-paneled conference room, facing a dozen high-ranking officers. His unauthorized test report is in front of the ranking admiral. "Lieutenant Commander Thorne," the admiral's voice is cold, "you have, in direct contravention of a superior's order, conducted an unsanctioned experiment. You propose we flood our own submarines. You risk catastrophic fuel contamination and unknown buoyancy dynamics, all based on a test on a piece of scrap." Another captain speaks up. "We have filtration systems, yes, but they are designed for condensation, not for gallons of seawater. What happens in a heavy sea? The water and oil mix. An engine chokes. The sub goes dead in the water. You're trading one problem for a much, much worse one." The skepticism is a physical wall. They see him as a reckless academic, a dam builder who doesn't understand the realities of combat at sea. Thorne takes a breath, his voice steady, channeling all his conviction. "Sight start. Admirals, the contamination risk is manageable. A simple standpipe on the fuel uptake, raising it 12 inches from the tank bottom, ensures we never draw the water layer. The sloshing is minimal. We are already accepting 100% risk. We know our boats are noisy. We know we are losing crews because of it." Sight 5. the Grunion, the Amberjack. They were detected before they could fight. This modification, he holds up his simple sketch, uses no new steel. It requires no shipyard delays. It can be retrofitted on any boat in 48 hours. It is just plumbing. And it gives our commanders the one thing they are begging for, the ability to hide. It gives them an extra 200, 300, 400 run feet of water. It makes the boat silent. This isn't a risk. It's the answer. There is a long silence. The Admiral stares at Thorne, then at the report from the Trout. Finally, he nods. Authorize a field trial. 1 boat. God help you if you're wrong, Thorne. The order is cut. The USS Balao, SS-285, the lead boat of her class, is chosen for the refit. Shipyard workers at Portsmouth, under Thorne's direct supervision, work around the clock. They weld 12-inch standpipes onto the fuel uptakes in the external bunkers. They drill and tap simple, open-ended 2-inch pipes into the bottom of each tank, the seawater inlets. The crew is briefed. They are skeptical. The new system is dubbed the compensated fuel system. Within a week, the Balao is on her first war patrol, heading for the heavily defended Japanese naval base at Truk Lagoon. Her official test depth is 400 feet. Her commander has been given secret orders. If pressed, he is authorized to exceed 500. Weeks later, the moment arrives. Contact, bearing 090, fast screws, sounds like a Kagero-class destroyer. The klaxon blares. Dive, dive, rig for deep submergence. The Balao pitches down, the control room filling with the tense quiet of the hunt. 300 feet. The Japanese sonar pings are sharp, metallic, right overhead. The crew tenses, waiting for the familiar, terrifying groan of the outer hull. 350 feet. Silence. 400 feet. The commander looks at his chief of the boat. Take her to 500. The diving officer repeats the order, his voice tight. 500, aye. The boat slips deeper, 450 feet. The pings are still there, but they seem confused. 500 feet. The Balao is perfectly, utterly silent. The crew listens. The external tanks, now full of an oil and seawater mix, are balanced with the crushing sea. There is no buckling, no pop, no groan. The depth charges explode, but they are distant. A dull thump, thump, thump far above them. The Japanese destroyer is dropping its pattern at 350 feet, the last known safe depth of an American sub. The Balao, sitting at 500, listens to the destroyer's frantic screws pass directly overhead and fade into the distance. In the control room, the commander lets out a slow breath. He looks at his sonarman, who is grinning. They are invisible. The Balao's patrol report is classified top secret. Operated at 500 feet for 3 hours undetected. Evaded 2 destroyers. Acoustic performance, excellent. The war in the Pacific has just changed. The consequences are immediate and profound. The order goes out to the entire Pacific Fleet. Olgato and Balao-class submarines are to be retrofitted with the compensated fuel system during their next overhaul. New boats under construction at Electric Boat and Mare Island have the system built in from the keel up. By mid-1943, the operational depth of the U.S. submarine force has quietly, unofficially, increased by 200 feet. Commanders, now confident in their boats, dive deeper, more aggressively. They run silent at depths the Japanese believe are impossible. The silent service finally lives up to its name. This single, simple innovation in plumbing has a tactical impact as significant as radar, U.S. submarine survivability rates increase. More importantly, their lethality does too. Boats can now trail enemy convoys, dive under the destroyer escorts, and surface in their midst. The acoustic betrayal that plagued the early war effort is gone. The principle of pressure equalization becomes a foundational element of all future submarine design. The reports from the field no longer mention anomalous, crushing noises. They are replaced by reports of successful evasion and targets sunk. And Elias Thorne, he receives the Navy Commendation Medal in a quiet ceremony. He is not promoted to admiral. His name is never in the newspapers. He is a Buship's engineer, and his contribution is buried in technical manuals. After the war, he is discharged from the Navy. He returns to his first love, civil engineering. He spends the rest of his career designing aqueducts and reservoirs in California, quietly managing the immense pressures of water, just as he had done in the war. His name is largely forgotten, his genius absorbed into the anonymous DNA of the modern submarine. Today, the principles Elias Thorne championed are not just standard in submarines. They are fundamental to all deep-sea exploration. The Alvin submersible, the remotely operated vehicles that explore the Titanic or the hydrothermal vents of the Marianas Trench, all use pressure-compensated systems. To survive the abyss, you do not fight it with brute force. You balance with it. The same challenge faces engineers designing habitats for the Moon or Mars. The pressure differential is reversed. A vacuum outside, life-giving pressure inside, but the problem is identical. The structure's greatest weakness is the difference between inside and out. The solution to the deep-diving submarine crisis wasn't a new exotic super steel. It wasn't a bigger engine or a thicker hull. It was a single counterintuitive idea from a man who understood water. It was the realization that to survive the ocean's crushing embrace, you had to, in a controlled and precise way, let the ocean in. You had to balance the external force with an internal one. It is a profound lesson in engineering, and perhaps in life. Sometimes strength is not found in resistance but in equilibrium. The USS Balao herself, the first to test this theory in combat, now rests as a museum ship in Pearl Harbor. Her steel tanks, which once silently held back the crushing pressures of the deep Pacific, now sit empty in the warm Hawaiian air. They are silent witnesses to a forgotten act of genius, an idea that gave American sailors a fighting chance by accepting the very element that threatened them. Every great idea begins as an act of defiance against impossibility. What impossible ideas do you think could change the world?